What's binding energy? Well, imagine you have you have a nuclide X, A, and Z. It's made of a certain number of protons, Z number of protons, and an N number of neutrons. Now imagine I give it enough energy so I can break the whole thing apart into pieces, into Z protons and N neutrons. Then you have to feed energy into it, right? In order to take it apart, to overcome their attractive force. How much energy do you feed to them? Well, the energy will be reflected in the mass gain. If you give it more energy, you give the system more energy, it's going to gain some mass. The total mass, after you break the whole thing down, would be Z times the mass of protons plus N times the mass of neutrons. That's the total after that, after you disintegrate them. The initial energy, initial mass, however, is just the mass of this thing, right? AZX. There is a difference in mass. The final mass is greater than the initial mass because you have to feed energy into the system in order to break it apart. That energy translates into greater mass. Okay. Now, we usually do not use the mass of each nucleus because it's much easier to measure the mass of the charged neutral atom, which includes the protons. Includes the electrons outside. Now, this is the mass of the neutrons. Okay, no electrons, just neutrons. Here, if I replace this with the mass of the hydrogen atom, how is that different from the mass of the proton? I'm supposed to use the mass of the proton, right? The only difference, really, is there is an extra electron here. So if you replace this with the mass of the hydrogen atom instead of mass of the proton, you will have an extra Z number of electrons. But that can be cancelled from here if you replace this M with the mass of the charged neutral atom instead of the nucleus. You will also have an extra Z number of electrons. So you see how they cancel out? So that works. Okay, so that will give you the mass increase. The mass increase, how does that translate to energy? You translate energy by multiplying by C squared, Okay, now how do you get that directly to MeV? If you multiply by C squared, and here times the mass, you just get kilogram and then times meter squared over seconds. That's cumbersome. How do you translate it directly to MeV, which is the unit we use most often in nuclear physics? Well, we know that 1U equals to 931.494 MeV over C squared. Therefore, C squared itself equals 931.494 MeV divided by U, right? So there we go. This is C squared. Okay, this is C squared. But the nice thing about this is that you measure everything in U here, atomic mass units, U cancel with that U, you just get directly MeV. So that's very convenient. Okay, this is the binding energy of the entire nucleus. In order to break this thing apart into pieces, that's how much energy you have to supply to it. The greater this energy, the more tightly bound the nucleons are. In other words, the more difficult it is to break it apart because you have to give it more energy, right? Now, what really matters is not the entire EB, binding energy, but binding energy per nucleon. Because if you have a large nucleus, you're going to have more nucleons, and of course the total energy it takes to break it apart would be more, right? So it's fair, it's more fair to compare binding energy per nucleon, and that is really an excellent indicator of how stable that nuclide is. And I have here a couple of very useful plots, both from experimental data. Here is the number of neutrons, and here's the number of protons, or atomic number. This line represents Z equals N. So you have the equal number of protons and the equal number of neutrons. And here I have what's called line of stability. Each dot that you see here represents one particular nuclide. All the nuclides that you see in this narrow band are stable. They are long-lived. They do not decay into something else very easily. It's called a line of stability. So you see here, for small nuclides without a whole lot of nucleons, they prefer to have N and Z equal to each other. Okay, same number of protons and the same number of neutrons. As A increases, as you get more and more nucleons, they prefer to have somewhat more number of neutrons than protons. So that is the line of stability. We can get some hint of nuclear structure from this line. Why is the line of stability like this? Why do they favor equal number of n and z, and then slightly more n than z, as number of nucleons get greater and greater. Another thing we can take a look is this famous plot. This is average binding energy, or EB over A, as a function of mass number A. Okay, so we start with very light nuclides going over to very heavy ones. You see, this curve goes up and it goes down. It's not entirely a smooth curve, but there are some jumps. Like helium, for example. It's particularly stable compared with its neighbors, lithium, and this is deuterium, H2. H1, there's only one nucleus. There's only one nucleon. You cannot break it apart anymore. So that's H2. But generally speaking, the trend is that it climbs up steeply, getting more and more stable, and then you reach the highest point. This is where it is most stable, and that in fact is iron. Iron is the most stable nucleus. And then away from that, you get heavier, it becomes less stable, but not as unstable as those. Because the curve goes up and goes down like this. There is a peak. Now, that means intermediate nuclides are generally more stable than really massive ones and really light ones. More stable means the energy of binding per nucleon is greater, which means if there's a way for me to change this type of nuclides to those type of nuclides, then the final product is here, more stable, which means lower energy overall, which means it takes more energy to break them apart, and therefore, in going from here to there, in breaking these larger nuclides into intermediate sized ones, you can gain energy. Energy will be liberated so that the final product is more stable. Okay, they sink into a lower energy state, releasing energy in the process. This process of taking larger nuclides and break it apart into intermediate pieces is called fission. Fission release energy. And on the other hand, I can take smaller ones, such as heavy hydrogen and helium, take these guys, and I fuse them together to reach this intermediate stage. And in this process, I can also gain energy. In fact, I can gain more energy per nucleon because the curve is steeper, right? You start from here, you end up there, instead of from here, end up there. This process of taking smaller ones and nuclides and fuse them together is called fusion. So fission on this side and fusion on that side. Either way, the final product is more stable, which means the final product has less energy than the initial product. Therefore, energy is released in the process, and that is the physics behind nuclear energy. And I don't think it's unfair to say, it's an exaggeration to say that the energy source of the future, of the entire human race, lies on this curve. Lies on this curve. Okay, whether we go through fission, which we're already doing, or through fusion, which we plan to do, we're working very hard to get, we will be able to harness nuclear energy, and that will give us almost, an unlimited amount of energy for many, many more years to come, instead of fossil fuel, which is running out very quickly. We'll see that in more detail in the next chapter, but here is the essential physics, this extremely important chart. Okay, so much for the experiment. We want to try to get some theoretical understanding of what's going on. Why do we have, the bonding energy like this? Why is it intermediate nuclei are more stable than the really light ones and really heavy ones, and so on? What's behind it? Can we find a nuclear model, just like the Bohr model for a hydrogen atom? Well, it turns out nuclear models, unlike the models that we saw for the atoms, especially the hydrogen atom, we know everything there is to know about hydrogen atom, and we know a lot about atomic physics, the electronic behavior of atoms outside the nucleus. Then we know inside the nucleus. Nuclear model is part of nuclear physics, and it is an active area of research even as we speak. There is not one nuclear model which is so incredibly satisfactory that nothing else matters anymore. We are going to discuss two competing models. They look very different. They each can explain certain aspects of the experimental facts, but we still do not have a complete picture of nuclear model. This is something different from atomic physics. And that has a lot to do with the complexity of what lies inside the atomic nucleus. We're talking about nucleons, each has a size, unlike the electron. And they're very close together, so the interactions among them are pretty strong. Uh, we cannot treat them as point particles very far from each other, so it's just naturally more difficult. However, we have some good intuition about what's going on, and so we're going to discuss two nuclear models that had gained a lot of experimental support. One of them is called liquid drop model, and that was proposed by none other than Niels Bohr himself in 1936. By the way, Niels Bohr's son, Asia Bohr, was also a great physicist who also won a Nobel Prize in physics, and he was a nuclear physicist. Now, the liquid drop model treats the atomic nucleus as a drop of liquid, it's very different from gas. In a drop of liquid, all these, let's say water molecule, water drop, all these water molecules are very, very close to each other, right? They can squeeze by, but they're not far from each other. And you can think of each one as a nucleon. So nucleons are really just pressing against each other. They're very close to each other. It's, instead of a gas, it's actually more like a liquid. So we get a liquid drop model. Okay. We are going to write down an equation, an expression for the most important quantity there is to know about the nucleus, and that is its binding energy per nucleon. Binding energy per nucleon. Okay, in fact, I'm divided by A, the binding energy per nucleon. The greater this term is, the more stable the nucleus is. Okay, now, you know that you've only discussed Coulomb force, then neutrons, there are no force between neutrons, okay? And the force between protons are repulsive, right? And by the way, you can forget about gravity, okay? The effect is so small, the gravitational force between nucleons, you can just totally ignore that. If you only consider electromagnetic force, you can never understand why these nucleons can form such a closely packed nucleus, because their Coulomb force will just repel each other to break them back to infinity, right? So whereas they get very close, there must be another force which simply takes over, and that has to be a very strong and attractive force. Yes, indeed, there is such a force, and it's simply called the strong nuclear force, or sometimes it's just called strong force. Why? Because it's so strong. It overpowers gravitational force. It overpowers the Coulomb repulsive force between protons. This is the reason why we can form a stable nucleus. And this is the only positive term here. Remember, the greater EB is, the more stable it is. And stability comes from a negative or attractive potential, and the only negative term here is due to the nuclear force. So this term represents nuclear force. Now, you can think of this as some sort of experimental finding. When you measure EB for all kinds of nuclides, many data points, you find this empirical formula works pretty well. Well, we can call it semi-empirical formula because we know roughly what's the physics behind each term, even though we do not completely know how to calculate this, because these numbers C1, C2, C3, C4 are only to be determined from experimental data points. We do not know how to calculate them by hand. Okay, so it's called semi-empirical. So without calculating C1, C2, C3, C4, because we don't know how to do that, let us at least try to understand what each term represents. What's the physics behind each term? Okay, now this term, the dominant term, it's greater than anything else, okay? All of these things combined. It is the only positive term. It contributes to nuclear stability. It is due to the strong, attractive nuclear force between any nucleons. It doesn't matter if it's a proton or a neutron. When it comes to strong nuclear force, the fact that you're a proton, the fact that you're a neutron makes no difference, okay? The only difference it would make is for, electrical force, but not for nuclear force. It's always attractive, and it's short-ranged. Short-ranged because only when the two nucleons get that close together, we're talking about 1 Fermi or so, will this force be kicked in. Otherwise, no such a force. You can imagine if the force always exists, then the two protons can be very far from each other and still attract each other, and that force is far greater than the repulsive force, electrical force. Then that certainly doesn't make any sense, right? So it's a strong but short-ranged force. What does short range mean? Short range means if you have a nucleon here, proton or neutron, doesn't matter. It is able to attract the neighboring nucleons. But what if you have, this is the nucleus, right? What if you have another nucleon here? It doesn't matter to this guy because this guy is too far from here. It is only able to interact attractively with its nearest neighbor nucleons. And so therefore it doesn't really matter how big that thing is. This guy cannot remotely act over there. Okay? So therefore, I don't care how many total nucleons you have in a nucleus. Each nucleon inside, in the interior, not on the surface, but in the interior of this nucleus, can only interact with a finite number of its nearest neighbors. The fact that you have a bigger overall nucleus does not matter because those guys do not see this guy, or vice versa. So, on average, for the interior nucleons, each can only interact with its a few nearest neighbors. Therefore, it can only contribute to the stability by a certain amount, which is limited by how many neighbors it has, but independent of how many total we have in the rest part of the nucleus. And therefore, this term is proportional to the total number of nucleons. Okay, because again, each nucleon can only contribute this much. It doesn't matter whether you have more, nucleons elsewhere. It's too far for these interactions to happen. So that is the dominant stability term. All these terms are negative, which means they are destabilizing factors. They tend to break things apart. Look at this. This is called surface effect. Remember I said if you're in the interior, you're surrounded by your all kinds of neighbors, right? So you can attract. But if you're on the surface, then you can only get attracted on this side, but not on that side, and therefore that nucleon do not contribute as much as this guy to the stability, right? Because it loses any attraction here. There's nothing on that side, and therefore the bigger the surface is, the less stable the nucleus is, because on the surface the bonding is not that strong. There's nothing on that side. And how much is the surface? The surface area S goes like r to the power 2, right? And the radius is r, and the volume is V is proportional to A. That's r to the power 3. Therefore, the surface area S, which is r to the power 2, should go like A to the power 3 over 2. Okay, A to the power 1/3, that's r, the radius. Then you square it, you get r squared, and that is the surface area. So that is called surface effect. It's a negative effect, again, destabilizing effect. Now, look at this term, z times z minus 1. Why z? Because this is what? The force between the protons. That is a long-range force. Every proton can interact with every other proton. This is such a short distance for protons, For electromagnetic interaction, you have to include every proton in it. How many proton-proton pair can we have? Well, for each pair, I have 2 protons, right? So how many protons can I choose for the first particle in that pair? I have z choices. Z is the number of protons. Once I choose one proton, there are this many protons left. So the total number of pairs is z times z minus 1 divided by 2. That 2 is getting absorbed into that constant. So that really is just number of proton-proton interaction. And the Coulomb repulsive potential goes like K Q1 Q2 over R being the separation between them. On average, the separation, we can use the the size of the nucleus to express that, which is R divided by R. R is a to the power 1/3. See that? A to the power 1/3. Okay. So again, this term represents the destabilization effect due to the Coulomb repulsion. It's destabilizing because it tends to break things apart, making EB lower. All right. What's the last term? This last term is a little bit interesting. It's n minus z here. What is n minus z? That's the difference between the proton number and neutron number. It doesn't matter whether it's positive or negative. You square it. It's also a destabilizing factor. So that means is that for some reason, the nucleus favors n equal to z. That will make this term go away. It will make things more stable. EB will be greater because it's a negative term. Why is it that the nucleus likes n to be equal to z? And there will be actually a destabilizing energy penalty if n is not equal to z. There is a negative sign. When n is far greater or far less than z, that's not desirable at all. That is called a symmetry effect. And it turns out that is linked to the Pauli principle. We'll see that in a minute, why we have such a term. Why is it that n equals z is more favorable, energetically favorable? Okay, turns out that for large enough nuclides, when you choose a set of numbers C1, C2, C3, C4 correctly, you can get a lot of correct values for the binding energy based on the same set of numbers C1, C2, C3, C4. Therefore, this semi-empirical approach makes a lot of sense. Okay, even though we do not know how to calculate C1, C2, C3, C4, each term has a distinct physical meaning, and it sort of represents at least part of what's going on inside. Therefore, it has a pretty good match. And again, if you use this curve, if you set a series number C1, C2, C3, C4, then you can actually have a smooth curve, okay, a smooth curve. And that smooth curve can include a lot of actual data points that agree with experiment. So again, fusion on this side, fission on that side, either way, you can reach the most stable intermediate-sized nuclides, and you can get energy out of it. All right, so is the liquid drop model foolproof? Are there things that it cannot explain? Oh yes, there are plenty of things it cannot explain. And for that reason, we need competing models. We need models that explain other things. The most successful competing model for that is called nuclear shell model. In a nuclear shell model, what we do is we study the energies allowed for these protons and neutrons. So it's kind of like a Bohr model, you know, in terms of energy diagram, okay, which is missing in the liquid drop model. Now we have to separate the neutrons and protons into two different categories because there are two different types of particles, but each type is identical, which means two neutrons are indistinguishable neutrons within the same nucleus, and therefore we have to consider the Pauli exclusion principle, right? Okay. Now, why is the shell model so useful? What did it accomplish? Because the shell model explains things that the liquid drop model couldn't explain, and that's the so-called magic numbers. Okay, magic numbers. What are the magic numbers? Well, it turns out that if either Z or N, proton number or neutron number, is one of these numbers, 2, 8, 20, 28, 50, and 82, you get a relatively stable nucleus on nuclides. And therefore, that means the total energy of binding is greater per nucleon. There must be something about those numbers. Can you explain why those numbers result in more stability? Well, the liquid drop model cannot do anything like that because it's a smooth function. Okay, it's a smooth function if you do that. There are no spikes. But according to the shell model, you have to understand why these spikes come from. For example, n equal to 2, that's helium. You know, if you go back to the actual experimental plot, look, helium, that's n equal to 2, right? Look, there is a spike. When you see a spike in this curve, that means this is particularly stable. Okay, so that's an example of a magic number, and there are other magic numbers. So the curve is actually not smooth. It actually has spikes, and those spikes, how do we understand them from the shell model? Well, first of all, in the shell model, as a good well, I shouldn't say a good approximation, as a starting approximation, okay, because I don't know how to do it in any other way. Let's assume that the interactions between neutrons among nucleons are negligible. That, of course, is wrong, okay, because these nucleons are so close to each other, we have to consider their interactions. But if they were not interactive at all, then we basically just put them in a box, right, in a very tiny box of the size of about 1 Fermi, okay? Now, even if they don't interact with each other, you put something into something that's small, they are going to have to go to different energy levels because particles in a box have different energy levels, and they cannot all cram to the same energy level because of the Pauli principle, right? So if you had one proton, this proton can go to here. It's a spin 1.5 particle. It's a fermion. If you had 2 protons, and this guy can go into here, and then and the third one have to go here, the fourth one have to go here, and so on, and so forth. Okay, and then you have another one. Say here is the Fermi energy for the protons. Neutrons are also spin 1.5 particles. They're also, therefore, they're also fermions, but they have their own set of energy values because they're not identical to protons. So here's the first neutron. It's going to be here. The second neutron goes to here. Third neutron, fourth neutron, and so on. Now, we can first we notice that the proton orbital energy levels are slightly greater than neutrons because you also have to consider the proton-proton repulsion, Coulomb repulsion. Neutrons don't suffer from that at all. So it's slightly more. Only slightly more because, after all, it's a strong interaction, the nuclear interaction. That's more important than the Coulomb repulsion. Okay. Now, we know from our experimental data that nature somehow prefers n to be equal to z, at least for small nuclides with small values of n and z. It prefers n equal to z. You can see why that's the case now, because what I drew here is a very different case. I have 7 protons and only 4 neutrons. I say this is not very good. Why? Because if you have a total of 11 nucleons, okay, 7 plus 4, right? Do you really want, well, let's say 5. Okay, so I give it an even number. It makes things a little bit easier. Let's say I have 12 nucleons. So that's 7 plus 5. So you see, z is 7 and n equals 5. They're not equal to each other. But I say this is not the best thing to do if you want to lower the energy to stabilize the system, because these levels are very close to each other. They're almost redundant. And if you have that many protons, the last proton have to go all the way to here. But if you take that proton and turn it into a neutron, so this time you have 6 protons and 6 neutrons, then this guy don't have to go to here. It can go down there, right? You see here? So basically you turn that guy from a proton to a neutron. So now you have 6 protons, 6 neutrons. That's the same numbers. That makes total energy less because you don't have to go all the way to here. So you see, by satisfying the Pauli principle, you can easily understand why nature prefers n and p to be equal, roughly. N and z to be equal, smaller nuclides. Smaller means the total number of n and z are not very large. But according to the curve, the line of stability, when you have a large number of nucleons, then it turns out that n equals z is not that preferable anymore. Rather, what you want is you want a little bit more number of neutrons than you have protons. So you see, the line of stability breaks away from n equal to z. The bigger the total number of neutrons, total number of nucleons, the more neutrons you would like compared with protons. And you see, that can also be understood from this curve, because after all, the protons and neutrons, they don't have the same energy levels. The protons go to a higher energy level. And this is the small effect for small number of z. Let's say z equals 3 or 4. You don't have a lot of proton-proton pairs, right? What if z equals 50 or 100, you know? That z is so large, how many pairs can you get? For example, if you have z equal to 100, we're looking at 100 times 99 over 2. Okay, that's thousands of proton-proton pairs. Even though each contributes a very little, you have thousands of terms that can contribute a lot. So when you have a lot of protons, then even if you pay an energy penalty by turning some of the by going from here to there. What I mean is, even if you have to pay a penalty by turning some of the protons to neutrons. Normally, you don't want to do that because that pushes the neutron Fermi energy high. You still gain an overall energy advantage because those Fermi, the proton-proton energy levels will push so high because of the electronic interaction, electromagnetic interaction. Okay, the energy gap becomes significantly wider on the proton side than the neutron side. So overall, it would then pay to get to have more neutrons than you have protons to reduce the destabilizing effect of the Coulomb interaction between so many pairs of protons. That's a qualitative understanding of the line of stability. Okay, so I write n somewhat greater than z, larger nuclides. It also explains why even numbers are the most stable. Even number means you have even number of z, even number of z, and even number of n. Because you see, I already have it here. I already have it here. That's an odd number, right? I might as well put another one here because it doesn't have to go to any higher energy. You see that? It doesn't have to go to any higher energy. If you have an odd number, that means the next one have to go to the higher level. It's a matter of pairing. Okay, if you form a pair, the energy of each one in the same pair is the same. You don't have to push any higher. Same thing happens there. So even ones are more stable, and even odd ones are better than odd ones. Okay, if you have an odd one and odd one, then why not turn this into here, or turn one into there, and then you have an advantage that way, right? Okay, so that's a shell model, but I have not explained magic numbers because it's not easy to explain, even with the mention of shell model. Suffice to say that this was a successful model that was introduced first in 1950. That's much later than the liquid drop model, and that was a work that received the Nobel Prize, earned a Nobel Prize for these two German physicists, and they were able to calculate to include not free fermions. Okay, that's too simple. They actually included the interaction between the magnetic energy dipole moment and the orbital motion of these nucleons, and it's a very strong interaction because we're talking about a very close proximity and nuclear interaction instead of just electronic interaction. And with that additional consideration of energy, they can successfully explain why these numbers correspond to more stable nuclides. So that is the primary success story of the shell model. They were able to explain the magic numbers.